Hello, and welcome to our video presentation of SFC. My name is Jivin B. James.
And my name is Daniel Alexander.
This program allows users to design visual structures such as two-dimensional trusses or bridges, and helps them to further solve the internal forces in them. Elements of the program mainly include simple matrices and structural arrays, which have been mixed with complex computations to produce the desired output. The creation of our program can be divided into 5 stages as displayed. The first stage was basic drawing implementation, which involved addition of joints, formation of lines and forces, and many other attributes. The next step was to visualize the above components in order to enhance the experience of the user. After this, we decided to further boost this experience by giving the users an option to create structures of their own materials. Stage 4 was by far the most difficult to overcome, and we will explain more in depth about this later in the video. The last stage was the debugging process, which also involved the addition of many side components. Our program has undergone a dramatic change over the timeline in this context. The main changes that can be seen are the addition of materials, a results table, and the displaying of coordinates. Now, to demonstrate the working of our program, we will build and solve the following truss. To create a truss, one must first enter the number of joints and their respective locations. This can be done by selecting the Create Joints button. The user is prompted to enter the X and Y values of each respective joint. Members between joints can be drawn using the Create Lines button. One must simply click on the 2 points between which the member is formed. Zooming of the truss as well as panning is also possible. Coordinates of the truss can be displayed, and the default view brings the SFC work window back to its original form. Users can add a new material and can also delete saved materials. They can also load previously saved materials, which changes the information on the top left-hand menu respectively. Depending on the material used, the center of mass of any truss can be displayed on the work window. The Add Forces button allows the user to add a force to any joint and prompts to enter the magnitude as well as its inclination with respect to the x-axis. Similarly, the Apply Anchors button allows the user to place an anchor, that is pin or roller, to any desired joint. Only 2 anchors are allowed in any structure. The static forces are then calculated by clicking the Solve button and displayed using the Results button. Users can save their trusses, can also load previously saved trusses. Deletion of trusses is also possible. Now we will explain the core of our program, unit vector solving.
And now we will explain the framework behind our solving algorithm. As an example, we will be using the same truss as before to visualize the procedure. However, this explanation conveys only a fraction of the complexity of the core of our program. Each member has an X and Y unit vector. These are easy to find but difficult to store appropriately. We first use an organization system where the rows and columns represented different joints being attached. As you can see, the line of zeros is caused by joints not being able to be connected to themselves. But this matrix is not useful for solving, since each column has different members with different respective forces. This meant that we had to find a way to organize matrices so each member has its own column. The index equation was found in order to create an index for each line, just like these 2 example matrices. Now, by transposing the X and Y unit vectors and stretching the matrix by using the previously found indices, we can create a solvable member force matrix. This is possible since now with this organization, each row of the matrix can represent an individual force equilibrium equation. In our program, our entire code was self-developed, besides MATLAB's automated code writing by guide, which was used to create our GUI. We faced multiple technical difficulties, such as solving and material integration while solving. However, we realized that through MATLAB's help documentation, we were able to combine our problem-solving skills with this information to overcome these boundaries.
Over the period of time that we were creating the program, the biggest lesson we learned was that MATLAB offers a wide variety of functions to make almost any type of program. The only limitation, but also the greatest advantage, is that we can manipulate these functions in any desired way to create our perfect code.